Welcome back. This module I will discuss about equation of continuity and equation of motions. So essentially these are nothing but the mass balance equation for a flowing system and the momentum balance equation for a flowing system, and we are going to follow the Eulerian approach of control volume here. That is conventionally done, and you should encourage your students to explain continuity and conservation equations for the 3D flow field, not limited to a 2D flow field, and explain where the components get in, etc. Okay, so first let us talk about the equation of continuity in the Cartesian system. I am deliberately following the approach of writing it here, which is analogous to the chalk and talk approach, and I guess it is always more effective than the PowerPoint if I construct the figures or write the expressions right in front of your eyes. And therefore, I also encourage use of technology is good, but these type of lectures you should try to construct the figures and try to explain things to your students as much as possible without using the PowerPoint. That is exactly what I am doing. So, this is a control volume which you all know, but please check your students are able to construct the control volume properly. So, you can so these are the dimensions dx, let us say this is dy or this is dy and this is dz. So, they might be having several questions on how this control volume is done. So, for example, you can highlight that the coordinate here is x, y and z, and then the coordinate over here would be x plus dx, etc., etc. So, for example, here this point will be x plus dx, y plus dy, z plus dz. We tend to neglect these minor details, and often this leads to pretty wrong concepts. So, what is going to happen? So, if we would like to write a general mass balance for a control volume, how would it look like? So, it would be like the most primitive form: input minus output plus generation is equal to accumulation. This is the most commonly known form. So, it can be mass in minus mass out plus mass generation is equal to mass accumulation. Now, we all know from the basic fundamental of conservation of mass that mass generation is not possible, right. Even if you have a chemical reaction, let me tell you, in classical fluid dynamics we do not talk about systems where you have reactive flow. You do not produce mass, you only produce some new species. The overall mass balance still remains valid, right. So, we need to worry about the input and the output terms. So, what is actually entering? Because of the flow, there is a flow, three components of velocity are u, v and w. You can choose to decide to choose whether you would like to teach in that vector notation or the tensor notation. It is all fine, but the basic physics should be explained to the students as the most important thing. So, if you look into the left face, what is entering is mass is entering the control volume only because of the x component velocity over here through the left face, and the mass that is entering is rho into u into dy into dz. This is the rate of mass entering because you have a velocity term which is per unit time, and this is evaluated at x. You can write it like this, and the mass that is leaving from the right face over here is rho u, or let me write it with full rigor, what I have written is the possibility of handling a compressible fluid also. So, if in case rho varies itself as a function of x. So, that is taken care by here in this particular term, and this you can simplify as rho u plus del x of rho u dx into dy dz. So, only the product containing the two partial derivatives have been neglected, because that is considered to be very small. So, based on these two terms you can find out the net efflux in the x direction, which is going to be this term. Let me write it once. And I encourage that please do not rush through these lessons to the students, because many times we take it for granted that they are all understanding, but reality is it does not happen. So, just write it once, the concept becomes absolutely clear. So, what happens is the first set of terms cancel out and you get only del x of rho u into dx into dy into dz. Now, if you look carefully, dx into dy into dz is nothing but the volume of the control volume, right. So, you can write this in a more compact form, del x of rho u into delta v, right. Similarly, you can find out the net efflux in the y direction as well as in the z direction, and you can find out that the terms are going to be del y into rho v dv and del z of rho w dv respectively. This is for the y direction and this is for the z direction. So, if you now look into the balance equation, so we have actually calculated the left hand side term, right. We have the total input minus total output, which is the efflux terms. So, we now need to worry about the accumulation term, and accumulation would be very simple. It is accumulation has to be with respect to time, del t into the mass that is accumulated, which is nothing but rho delta v, rho dv, which is the volume of the control volume. So, or in other words, how the mass of the control volume is changing with time. So, if you write the full equation now, you will get you can bring out this dV out of the differential, because it is not a function of time. Control volume, the volume or the size or the dimensions of control volume do not change with time, right. So, what you can do is you can cancel this dV thing, the total volume of the control volume, and you get the conservation equation, which looks like this. Now, at this point you can introduce the concept of incompressible fluid, which tells rho is not a function of x, y, z and t. So, it does not vary spatially or temporally. Now, that is very interesting. So, what it means if for and you can also tell that the most of the problems that we handle for incompressible in chemical engineering fluid flow problems, they are okay to be considered as incompressible fluids, and therefore, the assumption of incompressibility is sort of perfectly valid. And therefore, if you take rho to be constant, so what happens is the right hand term goes to 0, and you can take out the rho out of the differential, and you get del u del x plus del v del y plus del W del Z is equal to 0. There is a very interesting catch. Actually, even if you have an unsteady flow with an incompressible fluid, you will still get this form of the continuity, because of the fact that your right hand side del rho del T term cancels out because of the definition of an incompressible fluid, which is rho does not change with time, right. So, this is very interesting. People have a feeling that this form of continuity is valid only for a steady state flow. That is not the case. Steady or unsteady, the moment you have an incompressible flow, this form of continuity remains valid, right. So, once we understand the functional form of conservation of mass or the continuity equation, and another concept that I would like to remind you at this point of time is the concept of substantial derivative. Let me just write it for the x component. Sorry. We are now in a position to handle the conservation of momentum equations, and that I will do in two ways. First, I will show you how it can be very easily handled by simply considering the nature of fluid acceleration, that is the concept of substantial derivative in Newton's second law straight away. However, for the benefit of the students, it is strongly encouraged that you again draw a control volume and show at each phase due to each of the velocities the momentum is actually getting transferred into the control volume. That will really help each one of them to have a very good concept on this particular matter. Okay. So, first thing what we would like to do is conservation of momentum is a direct consequence of Newton's second law. So, momentum equation, Newton's second law tells that this is it, what it tells in the vector form. Where P is the linear momentum and we also have for a system P is equal to an integral for mass V d m. For a system with infinitesimal mass, dm, we can write the Newton's second law as df is equal to dm into dv dt for the system, right. A little bit of vectorial notation I have used from Fox McDonald, but you can also do it in whatever way you would like to. Now, you can handle the case in two ways. You can straight away say that for a flowing system, based on your knowledge of substantial derivative, this is nothing but dv dt. This is the reason why I was emphasizing the concept of substantial derivative so much, because for a fluid you always have convective or the spatial acceleration in addition to the temporal acceleration. So, once you write that, you can simply have df is equal to dm into the expression for the substantial derivative and then you can sort of look into any one of the components to, because I have been following in the scalar notation. So, if you decide to look into the x component, for example, then you can simply write that dfx into u del x plus v del u del y del t and so on. Of course, at this point of time you need to worry about what are the if the forces acting in the x component, right. So, again you can generalize them to be the two types of forces, those are the body force and the surface force, and of course, the typical example of body force is the gravity that is acting on the fluid element or the flow field, and surface force are the stresses, which we are going to come soon. Of course, you should encourage your students to think of what are the other, what can be a second example for body force as well as surface force, and if there is an electromagnetic field, that is of course an example of a body force, or if you have a microfluidic flow and then there are strong surface effects, that is going to be surface force or surface tension sort of is the second surface force. So, then you can simply expand this term to and then you can look into the stress individual components. But before that, I sort of would now do what is nothing but actually a shell balance, which I sort of discouraged you to do, but at this point of time if you write that in that fashion, that actually helps the students to have a feeling of how the momentum is actually getting transferred into the control volume. So, I will take the same control volume that I have taken in the context of discussing the conservation of mass, so that everybody is conversant with what I am using. So, this is again the same control volume, right. So, we have this dx, this is going to be dy, and this is going to be dz. Now, you need to understand that when we are considering the conservation of momentum, we need to consider the momentum for every direction. So, the example that I am going to highlight, you can do this in your class and the students will really like it, is the conservation for the x direction only, right. So, what are the things you have? You have the flows, this is the x component flow, you have an y component flow somewhere over here, you have a z component flow somewhere over here. Now, let us consider about the left face. So, what is the momentum that is entering? Because if you would like to write a balance for momentum, so the net exchange of momentum, rate of change of momentum is proportional to the statement of Newton's second law, right. So, what is the momentum that is entering the left face? And the momentum that is entering, what momentum is entering? We are considering the momentum balance for in the x direction. So, we are considering the so called x momentum. So, you need to understand the momentum that is entering through the left face is u into rho u, right. Momentum is mass into velocity. Here what we have for a flowing system is the mass flow rate into the velocity. So, rho u is the x momentum over here, that is the mass flow rate, and this u is sort of the carrier that is pushing the momentum into the control volume at location x. Similarly, so this is the momentum in from left face. Similarly, you can calculate from the front face what is the x momentum that is entering, and what is entering is, this is the momentum that is the mass flowing due to x component velocity at the front face, and it is because of the v component velocity over here or the y component velocity over here, the momentum gets pushed in, right. So, you have a term which is like V into rho u evaluated at y. In fact, if you look very carefully in the handout, I will make all these details. We typically consider the rho u to be at the center of the control volume, and you consider the individual u, v and w's at the respective faces, right. Similarly, you have a third component of momentum which is entering through the bottom face and which is going to be w into rho u evaluated at z. And or if you decide that the centroid of the control volume is x, y and z, let us say the centroid then actually the location over here becomes x minus dx by 2 y z. So, you can write all these things very carefully, and so this is actually the momentum that is entering. Of course, you have to multiply it, that is something I missed out with the cross sectional area, which is going to be dy into dz, and in this particular case it is going to be dx into dz, and this is evaluated at x y minus dy by 2 z, and similarly this will get multiplied by dx dy, and this is evaluated at x y z minus dz by 2. Similarly, the momentum that is leaving, you can calculate that to be dy dz. Again the expressions remain same. So, rho into u into rho u evaluated at x plus dx by 2 y and z and so on. So, these will be evaluated now at x y plus dy by 2 and z and so on. Kindly refer to the handout. So, this sort of now, if you sort of subtract these individual terms, you can get an idea about the net momentum that is entering, net x momentum that is entering the control volume due to the three components of velocity. That is the most important thing. When you are talking about the x component conservation equation, all the three velocity components are active, but you are focusing only on the x component of the momentum. So, momentum we are looking into is the rho u for this particular control volume evaluated at x, y and z, and that momentum is pushed in by the x component velocity, by the y component velocity and the z component velocity. That is the most important thing, right. So, when just one quick clue you can give to your students, when we are talking about the y component balance, for example, the same front face, then we will worry about the y component momentum being pushed in by the y component velocity, and the left face where the x component x momentum was pushed in by the x velocity, in the context of y component velocity, it will be the y momentum, that is rho v, will be pushed in by u. It goes something like this. In fact, this is apparently a futile exercise, but if the students understand this concept, this will make the entire concept of momentum balance very, very clear to them. So, I will encourage you to sort of, though we have the complete advantage of understanding substantial derivative and using the mathematical form of substantial derivative in getting the conservation equation, I would request you to sort of explain this momentum transfer mechanism, or what is the momentum we are talking about and which component of velocity is pushing it in or out of the control volume to the students, because that will really make the concept clear. So, once this is done, now we need to worry about the individual stress terms, and so again if we look into the x component balance, what we have is, we have a normal stress acting over here, and because of the x component x directional flow, I am not again worrying too much about the signs which automatically will fall in place. You have two additional shear stresses over here. And if we now correlate to the concept of angular deformation, so what tau xy does, tau xy, if you remember, we have already talked that it causes a deformation in xy plane. So, here you actually have an xy plane. So, this is the consequence of the x component velocity, right. So, if u over here and u over here at the left face and at the front face and the back face are different, they are going to sort of try to deform that particular plane, and that is the genesis of the xy stress due to the x component velocity. There will of course be another component of xy stress that will be due to the y component velocity. So, you now understand that this component of shear stress we are talking about is the one that is del u del x and the del u del y. In contrast, the other one which will be contributed by the y component velocity is actually the del v del y, and of course, it is a 3D element. So, the total stress will be a summation of the the summation of that angular deformation, which tantamounts to the summation of the velocity gradients. That is the total stress this particular xy plane is going to experience, right. So, we can make a balance, coming back to the x component, we can make a balance of the stress terms, which are the normal stresses plus the shear stresses right. So, this of course, you need to multiply with the cross sectional areas, and therefore, the total stress tantamounts to be Of course, one thing I have not talked about is the pressure gradient, and I will not specifically talk about the pressure gradient also, because in advanced transport process I would like you to give the idea to the students that stress, any general form of stress can have two components, which are the deviatoric component and the hydrostatic component, or the component of stress that is related to deformation and the component of stress that is not related to deformation. I will just briefly mention about that here. So, any tau I j, please refer to the handout for more detail, which is sort of can be split due to tau I j deviatoric and tau I j hydrostatic, and you can do a little bit of detailed mathematics. So, this deviatoric stresses is related to the velocity gradients, let us say a generate velocity gradient like this, and this you can split up into the symmetric and the antisymmetric part. All you do, what it means is, these things sound very well, but you can sort of explain things very nicely. You just add and subtract half del u j del x I. So, this you can see the first term is related to angular deformation, the second term is related to rotation. We understand that rotation does not cause any shear stress, so angular deformation causes the shear stresses. So, the deviatory component is related to angular deformation, right. So, it is related to the rate of deformation, and based on a bit of mathematics one can get a more rigorous expression for that, which is not required, which is actually I will write all that down in the handouts. But what is more important is the so called hydrostatic component of stress, which is independent of any deformation. And a very good example is if you take 2 or 3 identical control volumes within a static layer of fluid. Of course, see the body force on each of them is going to be same, but however, since they are at different depth and the pressure distribution here is purely hydrostatic, they will be subject to different levels of normal stresses in this particular direction, and which is not related to any deformation, because since there is no flow, there is no deformation. So, this hydrostatic this is called the hydrostatic component of the stresses, and which is related to the pressure that is acting or the pressure gradient. So, kindly refer to the handout for the details of this. It would be very good if you can sort of introduce this concept of, so essentially the pressure gradient becomes a component of the normal stress, and if you expand this particular term into the hydrostatic and deviatory components, then depending on the situation you will have the appropriate pressure gradient. So, I think I will stop here, and so what we discussed in this particular module is the conservations of mass and conservation of momentum. Of course, this whole concept you can teach in a vector notation, or you can extend it for the other directions for the understanding of the students, and it is up to you which medium is going to work the best. Thank you very much.